Good afternoon, everybody. I want to go ahead and get started so we can give Dr. Bergtold as much time as possible today. Thank you for joining us. I have just a few housekeeping items before we begin. If you have questions throughout the webinar, please feel free to enter them into the chat box, and we will repeat them for the speaker, Dr. Bergtold. We'll encourage you also to tweet questions if you have them to MAB Webinar with the hashtag, so hashtag MAB Webinar, and we'll go ahead and enter those into the queue. Also, if you did not receive the material, the files that came yesterday to email, please send me an email at dkohl@ksu.edu, and I will get those out to you more momentarily. So again, thank you for joining us today. I'm Deborah Cole. I've had the pleasure of serving with the MAB program for the last 8 years. My background is in student services and education, and I earned my master's degree at K-State in 2002. Our webinar today is sponsored by the Master of Agribusiness program. Established in 1998, our flexible hybrid program tailored to individuals working full-time in all areas of food, agriculture, and animal health has reached more than 500 students. We were the first distance degree program in the country that was focused on the business and economics involved in managing production, agriculture, food, and animal health companies. And most of you all know this because you are MA. I do want to point out that all of our students do come to us with a bachelor's degree, 2 years of professional experience, and having completed prerequisite coursework. None of that has changed within the program itself. Our students come from all over the food and agriculture sectors, and we have seen an increase in our animal health representation. So if it's been a while since you've been with the program, that is something to keep in mind. And we know that the companies that hire our students or hire them away indicate that the skills that they have while they're in the program directly impact their teams, divisions, and companies in a positive way. And our webinar today is part of a strategy to help our students and alumni be MAB for life, to keep the skills and tools that they've learned in the MAB program fresh. So to that end, let me turn it over to Dr. Bergtold, and we'll go ahead and get started.
So just kind of introduce myself real quick. My name is Dr. Jason Bergtold. I am an instructor in the MAB program, and I teach linear and nonlinear programming tools. And I am also, I do research in the area of crop production, land use economics and conservation, and bioenergy. And I've been at Kansas State University since 2008. And so what I want to talk about today is looking at the upping our game on supply chain and logistics, and kind of as a retooling webinar, look at a specific problem and an introduction into Excel and use of Solver. Kind of remind you, if you've been in the program, what that's about. If you're new, give you an idea of how it can be useful. And so I chose to focus on one specific application to provide it more useful and kind of extend what has been seen in the MAB program so far. So in terms of today, I'll provide a basic introduction, look at operations research and logistics, network linear programming problems, and then we'll spend most of our time on an application in Excel to kind of learn the tools that we can use. In addition, please feel free to ask questions if you have them. In terms of as you have them, and we'll try to answer them as we go through the presentation. In terms of an introduction, a question that often arises are the tools that can help us to make better decisions, and that's really where operations research and mathematical programming, which is what we're looking at today, can really help to improve our decision making. And it is a support tool, not just it doesn't give us all the answers, but it helps us in improving our decision making. And so the idea here is to make use of the data and information we have at our hands to make better decisions. But whereas we're going to see this is not without a cost, there is a learning curve. This field of study that I teach and I present in my MAB class is operations research, or OR for short. By definition, OR is the discipline of applying advanced methods to help make better decisions that can be tailored to problem situations or businesses. In essence, it's using mathematical computer models and programming to help with decision making, to optimize different objectives or competing objectives for managers, decision makers, policymakers, and so on. It also can be used to look deeper into processes in manufacturing or in different industries to kind of learn about those and find potential inefficiencies and sources for improvement. So what I want to focus on today is one particular application of OR, and that is in the area of transportation and logistics. So these, in general, what we'll learn is this is a type of what we call a minimum cost network flow model, and that'll make more sense here in a minute. But, or in more general, these are what we refer to as network models. And these include a whole host of different types of problems. It's our basic transportation problem, or transshipment problem, but also includes problems such as maximum flow. So how do we move product through pipelines, determining optimal location of facilities, supply chain logistics, scheduling problems, and so on. And so there's a lot of different types of problems that can be modeled within this context. And that's kind of, I want to give you kind of the basic feel for what these types of problems look like and how we can solve them. So we're going to focus on two problems today, the transportation problem and the transshipment problems. And these primarily deal with the movement of product from suppliers or producers to consumers through a supply chain and potentially different level along different modes of transportation. In general, I do want to emphasize this is a mathematical problem. So this is based in mathematics. We're not going to spend our time developing here all the mathematical formal formulations of these problems, but just recognizing that these are mathematical problems. And we're going to be dealing with a type of this called a linear programming problem. And recognizing that there is a whole science behind solving these problems. And that is the field of OR. But what I want to focus on today is the development and solution of these problems and how it's applicable to different situations. So in terms of problem formulation, there's I teach a three kind of step approach. And it's answering these three basic questions. And so in the real world, we don't have a problem written out for us like we will today. And so how do you approach formulating these types of models and solving them? And the first question is to ask yourself, what is the objective? What's the goal in mind here? And then defining that objective in terms of a optimization criteria, such as maximizing profit or minimizing cost. Then once you kind of have that laid out, you can then ask the question, what can you change? So what are the levers that we can pull to meet our objective? And these will identify the variables in the model that we want to determine the optimal level for to meet our objective. So that could be determining the number of products to produce to maximize profit per se. And finally, one of the most important parts is that third step, what limits us? What are the constraints that are particularly pertinent to the problem in terms of defining the situation? And so we don't want to get so complex that the model gets unwieldy, but we want to include all the pertinent constraints. And so the constraints are important because they define the environment in which we're operating. And they're what really bring reality and kind of the real world situation into the problem. And so the reason I focus on these three questions and answering them, it actually helps you set up the spreadsheet model, and it's less redundant than other approaches, which take multiple steps and are a little more cumbersome to kind of get through. And so it's really the answer to these three questions that define what a model is going to look like. And we'll see that when we lay out our problem today. In terms of the transportation logistic models, this is a little bit busy, but what I want to do is spend a minute here is what's unique about these types of problems is that we can set them up with what we call a network flow diagram. And this is a much easier way to represent these models. And the idea is it shows the network that you're transporting stuff through. And it's made of different components. So usually we have a number, one or more supply nodes where product originates from. And then the idea is to get it through a network. You can think of this as a map through different locations to a demand location. So this could be our plant. Our demand locations are the retailers per se. And the intermediate points, which we call transshipment nodes, or these intermediate nodes could be like warehouses or distribution centers. And so the idea is to move product through the network at minimum cost. Along these, between each of these nodes, from what we have called supply nodes to demand nodes and transshipment nodes, we have these directional arcs that tell us the direction that product can move through the network. And these could be actual routes, and along each one we have a marginal cost that tells us how much it costs to move one unit of goods along that arc. And so that provides us quite a bit of information in terms of setting up our objective of minimizing costs. And so we have these directed arcs along with this cost of transport. Finally, in the network, we have these numbers here. So the negative number here actually represents supply. That's the amount of units we have available, and we need to meet this demand at these two demand nodes in this particular network, which is given by the 400 and 500 here. So the network really diagram is a unique way to set up our problem that shows us where a product's originating from, where it needs to go, the pathways we can use to get it there. And it also can be for each mode of transportation and the cost of you moving it along each of those arcs or pathways. And so this is a really unique, in essence, why the network flow diagram is important if you can draw them out. One, it helps conceptualize your problem, but second, it also helps you to create all the pieces you need to develop kind of the transportation, logistic, or these network models that we're going to see today. In terms of how do we go from this network flow diagram to a model, I'm not going to go through the math, but what are the three components of the types of models that fall from these network flow diagrams? In general, we call them minimum cost network flow problems. That's a really big word, but in essence, it's just a math programming model that we're trying to move product at minimum cost. The objective is generally to minimize transport costs by deciding our variables or how much to transport along each of those arcs or pathways between different locations or nodes. And so we're trying to determine these optimal shipment amounts between these different arcs. And finally, we have constraints. In terms to make the problem work, we have a unique set of constraints called these net flow or network flow balance constraints that really make the model work, that drive those shipments. We can also add bounds along these pathways if there's a maximum amount that can move. We can build in many other types of constraints or limits, such as if there's weight limits, transportation limits, production constraints, and so on. And finally, we have this condition down here, which I usually teach in my course that's implicit for most economic problems, non-negativity. We want to make sure our variables don't take negative values. And so we have this constraint here that it's a box we check in Excel, but to ensure that we're only shipping positive amounts. And that's just, most variables in economics are either 0 or positive. And so this is that general network model that we're going to look at and we're going to build in Excel. And so I just kind of wanted to give the general formulation here of what that's going to. And so what we want to do is take a problem we can set up as a network flow diagram, build it into a mathematical model in Excel, and solve it to find an optimal shipment path for product. I do want to bring up, in terms of we're using Excel to solve our problems, there are many other software packages. Probably one of the most commercial ones that is used is what is called Ilog. This is a software built by IBM. It's a powerful software package built on unique algorithms called Cplex, which IBM designed. And this Ilog has been expanded significantly to deal with a whole host of problems. You can code in it. It's plug and play as well, in terms of you can build it using kind of design tools they already have, so you don't have to program it out. And it can solve a whole host of different problems. The image I gave you in here on this, what's unique about the Ilog software is you can import like maps, transportation networks for different types of transportation systems for building these logistics supply chain models that are not only US, but global in nature. So you can have shipping pathways, air, truck, and so on, and rail. And it will actually build the connections and do a lot of that GIS work that you may need done internally. And so I just wanted to point out there are other software packages available in the market. And if this is something you're really interested in, I think this is a unique package potentially to look at. So with that, what I want to do is spend most of my time in Excel today. And so if you do have questions, please email me or drop it in the Dropbox, and I'll try to get those answers as we go through. So this is where I'm going to slow down a bit and kind of spend more time. And so the problem I want to focus on today is what we call transshipment problems. So this is one specific type of problem of that minimum cost flow network problem that we saw on the slide. The objective of the transshipment problem is to minimize the cost of transporting goods. And so a common application of this is the transportation of goods through a supply chain. And so this is the type of problem we want to focus on and look at. And so what I've done is kind of built an applied problem that we can walk through, look how the spreadsheet model is set up, look at the different components of the problem, and look at how we actually solve that and analyze the solution. So the first thing I want to look at is kind of an example problem. So we're going to look at a problem for the agricultural company that produces equipment used primarily for crop production. However, management has decided to subcontract the production of computer components needed for the equipment. They have 3 vendors that are available to supply the needed computer components, and the price for each shipment of components of 1,000 computer modules is shown below. So they can buy 1 unit or 1,000 computer modules from each vendor for the following prices here, from $22,500 to $22,700 and $22,300. In addition, we're provided the information that each vendor would charge a shipping charge. Each shipment would be to one of the company's 2 warehouses until it's needed for tractor production. So the vendor ships it to a warehouse where it's stored until it's needed for actual production. Each vendor has its own formula for calculating the shipping cost based on the mileage to the warehouse, and this is done through trucks. These formulas and the mileage data are given below. So these are the vendor formulas. They're linear formulas based on how far the shipments are going. And there's a base charge plus a mileage charge, and this is the distance between each vendor and the warehouse. So we can use these formulas, then calculate the transport cost between these vendors and warehouses, and I'll show you that on the next slide. Whenever one of the company's 2 factories needs a shipment of computer modules for tractor production, the company hires a trucker to bring the shipment in from one of the warehouses. So they're going to ship from the warehouse to the factory. And then there's a cost per shipment of doing this, along with the number of shipments needed per month at each factory. So we have a monthly demand of what's available, what's needed each factory. We have the warehouse shipment cost for that truck to move between the warehouse and the factory. In addition, we're provided information that each vendor is able to supply as many as 10 shipments per month. However, because of shipping limitations, each vendor is able to send a maximum of only 6 shipments per month to each warehouse. Similarly, each warehouse is only able to send a maximum of only 6 shipments per month to each factory. So the management of the agricultural company wants to develop a plan for each month or in particular, based on this information of how many shipments that should go to each warehouse, and then how many shipments from each warehouse should be sent to each factory. Our objective is to minimize the sum of the purchase costs, including the shipping charge and the shipping costs from the warehouse to the factory. So we want to minimize total cost, which is our objective. We know our decisions here, which are kind of outlined here, are those shipments between the vendors and the warehouses and the factories. And we know our constraints are going to be centered around the flow of those shipments, as well as the demand here, taking into account the net flow will build in the demand and supply that's available at each of those locations, as well as these upper bounds on how much that can ship, these 6 shipments that can be shipped between these different locations. So we can model this out using a network flow diagram, and I've drawn that here for you on the 3rd tab. So notice for our network flow diagram, we have 3 supply nodes, V1, V2, and V3. And we put our supply as a negative number, and there's a reason for this, but this is just the convention for this formulation. We represent this as a negative number. This is the amount that's available at each of these vendors, so 10 units. Remember, a unit here, and I wrote this at the bottom, is 1,000 computer modules. There's 2 transshipment nodes, warehouse 1 and warehouse 2. And we have 2 demand nodes, factory 1 and factory 2, and you have the amount that's needed at each of those, 10 and 6. In terms of the cost of shipment, so we have each arc, so each vendor can ship to each warehouse can ship to each factory. Those are our directional arcs, so we have a total of 10 directional arcs. Along each arc, we have the cost, we put the marginal cost of shipping a unit of the good. Notice along each of the arcs here, these 6 amounts, we have the shipping cost plus the purchasing cost. And that's why we have both of those numbers. And then the marginal cost of shipping from the warehouse to the factory is that trucking and hiring a driver, and that's given here for these individual transportation costs. Notice also along each arc, I've added an additional amount where we have this less than or equal to 6, which represents the upper bound in terms of the amount that can be shipped along each arc. And so for this purpose, we have a maximum number of 6 units that can be shipped along each of these arcs between this kind of simple supply chain that we have built in this example. Below, I've also taken, and I've built here, I've kind of calculated those costs. So using those linear formulas, I calculated the costs. I programmed the formulas in here for each company to calculate what the marginal cost is shipping between locations. And so remember, this is based on the mileage from the vendors to the warehouses, and these are the total costs that are calculated for this example. Are there any questions so far? So what I want to do is notice that the network flow diagram encapsulates all the information we had on the prior slide. And that's one of the reasons I think the network flow diagram provides a good basis of how to visualize and then use that to set up our problem. And we'll see where that connects and why we do that as we build the components. So what we want to do now is build our mathematical programming model, which is going to be what we call a linear programming model. All of the equations will be linear, and we're going to do this as a spreadsheet model used in Excel, and then we're going to solve that using Solver. So Randy Hobart on the chat asked, the upper bound is considered an assumption. And so, yes, here that is correct. So the upper bound here, that's something that could be determined at the factory as well. And so one thing here is that could be based on limitations, the docks at the warehouse and factories. So It could be an assumption, or it could actually be based on real life limitations. And so, but then Randy also mentioned we should probably challenge assumptions. And I don't know if challenge, Randy, I agree. I don't know if challenge is the right word, but the way we do that in math programming, and I'll show you here in a little bit, is once we get a solution to this problem, we can look at to see if these different constraints are actually binding, in the sense that do they limit the solution? And so we can play with that upper bound and increase it or decrease it and see what happens to the optimal solution that we obtain from the model. And that is what we call sensitivity analysis. And I'll touch on that in a little bit. But one of the things here that is interesting is likely an upper bound. If you had these would be determined a priori to the problem. And then what you'd want to do, one reason potentially to not necessarily challenge, but look at that is, would it be advantageous to increase the amount of space we have for taking in shipments or the movement of products? And so that's something that could be done and is very useful. It's one of the biggest benefits of using these models, is kind of asking what if once you solve the original problem. So let's look at now building the math programming model. So the first step in doing this, so we kind of went through the questions. We know our objective. What is our objective? It's to minimize total shipment costs plus purchasing by choosing the amount to ship along each of those pathways in the network flow diagram. And we know our constraints are the net flow constraints and those upper bounds. And so what we want to do is build each of these components. So why you answer those three questions first is, once you have those answers, that's where you start then. It's the answer to the second question is where I usually start to build the spreadsheet model. And so the first component to build in the spreadsheet model are what we call decision variables. These variables are the actual levers that the model is going to use to meet our objective. So the first step in formulating is to designate a cell for each decision variable. Okay? For a rule, you need one cell for every single decision variable. And we initialize these cells at 0. So when you create them, we designate a cell here and we make it 0. Okay? In terms for a transshipment problem, one of the reasons you do the network flow diagram is, in our model, we're going to have one decision variable for every directed arc. And so notice the labels on these are to the right. These are the arcs that product is moving between in our model. And so we're going to have one decision variable for every single arc in the problem. Okay? And that's a general rule. Okay? And so we have a total of 10 decision variables. On each of my slides, I tried to do this and have the information available for what I'm doing. You'll also see on each of these slides, I do include some of these building notes. And so you'll notice I do designate the cells here, but my labels are to the right for each of those arcs in this, okay? And so one thing I like to do in these models is I do color code as well. And I tend to use different colors to designate the variables, constraints, and objective information. I do like to label enough so that when I look at the model, I can see what's going on. And so labels are a good thing, and writing in comments as you need to as well is a good habit to get into in building these models. And so one thing that does come up is I have people have modeled this by model complete pathways for these problems. And I think one of the downsides of that is, if you have constraints on individual arcs in the model, doing a complete pathway from beginning to end and all potential pathways is, one, you could make the model bigger than it needs to be, and two, you can restrict the type of analysis you may potentially be able to do based on restrictions that could vary on specific paths within the network itself. And so while this is another way to set up the problem, I kind of recommend doing each arc as a separate variable in the model instead of kind of doing an entire pathway from beginning to end. So these are the decision variables in terms of setting up to the model. The next step is, once we have our decision variables, is to look at the objective information. So one thing we're going to need is a cell that actually calculates our objective function, okay? And so it's required that you have a cell that does this in Excel. This is, Solver is going to call this an objective or target cell, and we need that where it calculates your objective function value using your decision variables. So just like you needed a minimum one cell for each decision variable, you need a specific cell for the objective function. I usually also designate a number of cells to bring in the parameters used to calculate the objective function. So notice I bring in the purchase cost from the vendors and the marginal cost that we came up with in the network flow diagram in our computations of moving a unit of goods, which in this case is 1,000 computer modules, between two different nodes in our network, or say from the vendors to the warehouses and warehouses to the factories. It's the sum of these two columns which give rise to our marginal cost here of moving shipments along each of those arcs. And so this marginal cost includes the purchase plus transportation costs, especially for the first 6 nodes. And so our total cost is the sum product of our marginal cost and our decision variables. Well, what do I mean by that? So our objective function is linear. And so to calculate the total cost, what we're doing is, since this is a marginal cost on a per unit basis, we need to multiply these marginal costs times the amount that is actually shipped along each of these arcs to get our total cost. So that's linear. It's kind of this variable times this variable plus this variable times this variable. And we could write that out. So if we write that out here, what you'll see is you'd get a function that looks like this. Okay? And so it's taking, and that's what we call a sum product, because first we do these products between a variable and a coefficient, and then we sum those products. And so you could write this out, or there's an actual command in Excel to do that for you called the sum product command, which is what I use in the model. And so these two functions are exactly the same that we have listed here. And so you'll notice I use the sum product of my decision variables and my marginal cost for each unit to get up to a total transportation cost here, which includes our production cost. Questions up to this point? So now we have our decision variables and our objective information. The next thing we want to build in is our constraints. And so I have 2 different tabs for this. The first one that we want to build in is our net flow constraints. The net flow constraints are what guide product through the network or through our transportation system or kind of shipping system, however you want to put that, okay? The net flow constraints take this general form of inflows into a node minus outflows to a node are greater than, equal to, or less than supplier demand at that node, okay? Where supply, remember, in the network was given by a negative number and demand was given by a positive number, okay? Transshipment nodes, in our case here, these are the warehouses, have a supplier demand equal to 0. In essence, they're not endpoints. They're not beginning or endpoints. So we don't want products staying there permanently. So we assign a supplier demand of 0. And so I build these network flow models here in a box below with a different color code. And then have these building nodes. So Melissa asked, are you using GPS modeling to calculate the per mile cost into the transport costs? So I would say, based on the formulas in the problem, yes. I think you could use GPS, you could use a transportation website or software. I know Google's done it. I think one of the benefits of using, say, GPS or transportation, the GIS maps and the transportation maps that are free from the Department of Transportation is, if you're doing trucking, you can build those costs based on gas mileage, but find routes that meet the trucking requirements or limitations if there are weight limits. So it will take the proper routes and build that into account rather than a kind of point to point. And so I would say, yes, it's using GPS, but it's basing it on traveling the road network. And Melissa, I hope that answers your question. In terms of, so jumping back here, in terms of the net flow constraint, so we're going to have, the first thing is one of the other reasons we draw the network flow diagram is that there's going to be one net flow constraint that governs the flow through each node, which means we're going to have one net flow constraint for each node. So notice I have 7 nodes in the network flow diagram that we designed here. And so I have 7 net flow constraints, okay? The net flow constraints, I'm going to calculate the inflows, the outflow, the net flow. We'll have a relationship in the supply and demand. So notice the supply and demand is pulled right from the network flow diagram. It's the negative, we have 10 supply at each vendor. Those are represented as negative numbers. Our transshipment nodes are the warehouses, and our demands are positive numbers at each of the factories. So we need to make sure of the 30 units that can be shipped in a month, 16 need to get the factories. The question for us is, where should they come from? So how do we notice? This is how I built them in Excel. At a minimum in Excel, for a constraint, you need a cell that represents the left-hand side of the constraint. For us, that's the net flow. And at a minimum, you need a cell that calculates the right-hand side. For us, that's a scalar or a constant value given by this column, but it could also be a formula as well. To calculate our inflows and outflows here, I'm using a command called the SUMIF, okay? For the inflows, the SUMIF is going to find the shipments into a node based on using column G, while for the outflows, the SUMIF is using finding the shipments out of a node using column E. So let's take, for example, warehouse 1. And let's look at how this net flow constraint is computed, especially for the left-hand side. So the inflows is this SUMIF statement. The SUMIF statement is looking down column G. So these are, sorry, jump back here for warehouse 1. So this is finding shipments inflows coming into node W1, which is warehouse 1. So it's looking for these shipments where we have a W1, okay? And so these are the arcs coming into W1. Those are the inflows. So it's summing those 3 rows in the decision variable column. So what the SUMIF does is it looks in this range for W1 and then sums the corresponding decision variables as the inflows, which is the amount coming from vendor 1, vendor 2, and vendor 3 into warehouse 1. Those are the inflows. Similarly, we use a SUMIF to calculate our outflows. And so these are arcs going out of W1. And so it looks down E. So it's coming from W1 or out of W1. And we're looking for W1 here, which is here. And so it's summing these 2 decision variables. And so notice again, it's looking at the range, E in column E, the from for W1, and summing those corresponding decision variables for the problem. And so our net flow in general is the inflows minus the outflows. And that's what we want, as we saw up here, for our general formulation of the left-hand side, okay? And this is going to be related to the right-hand side, which for the warehouse constraint, which is a transshipment node, would be 0, okay? The question is, what is this relationship? So constraints in these problems, or in general in a math programming problem, can be greater than, equal to, or less than or equal to. Commonly, they're inequality because most of the time they're resource constraints, saying we have a certain amount of resource we can't use over. So that would be a less than or equal to constraint. In terms of for a network flow model, it's these constraints that govern the shipment. And this is based on a simple relationship here. So what you need to do is add up total supply and total demand and look at how they're related in the network. So in our case, we add up total supply, which is 30, and we treat these as the absolute value, and total demand is 16. So total supply is greater than total demand. So in general, the rule is to make all of our net flow constraints then greater than or equal to. If total supply equals total demand, the constraints are equality. And if total supply is less than total demand, these would be less than or equal to constraints. So questions on setting up the net flow constraints? So the other constraints we need to add in here are the upper bound constraints. So it may be the case there's a limit on the number of shipments that can be made along an arc, and so we build these in as upper bounds. To build these in, I actually just build in an upper bound here. And so I'll actually add this constraint specifically in Solver, but I want to build a column here that tells me the maximum amount that can be shipped along a particular arc. So this upper bound is for each of these arcs and on these decision variables. And so that's how I build that in, okay? This in essence establishes our model for this network problem, or this transportation or transshipment problem. And so what we want to determine now is how do we solve this, okay? So this is where we use Solver. So this is kind of where it gets interesting once you've built the model. And so Solver is going to look something like this. I do have the general kind of how to build your Solver here rules. And so to solve the model, we're going to use Solver. The Solver in essence is the algorithm that Excel is going to use. It's provided by Frontline Systems. And it's what's going to solve this problem. So it's going to determine the optimal level of these decision variables to meet our objective, satisfying our constraints here, okay? The Solver add-in does have a limitation, and so I'll show you that here. Designed for research, but is open to the general public. And this is available at opensolver.org. It doesn't look exactly the same as the solver we're going to see today, but it is very similar, okay? The nice thing about this is not limited by capacity as much as like the regular solvent. I don't say it's going to be as flexible either as the premium version, but it might work if you're not looking for too big of problems or too, say, non-linear if you get into those types of problems. So for us, we want to look at Solver. If you don't have Solver on your computer, you can find the built-in version by going to Options and going to your add-ins. Down at the bottom, you'll see this Manage Excel Add-ins. You'll click Go. You'll just want to click the checkbox here and hit OK. Solver will show up in your Data tab up here. And so that's what we're going to click here is Solver. So now we need to set up the problem in Solver. So I'm going to go ahead and reset this so we can walk through it. So this is the Solver. So we're setting up the model for us. So notice you need your set objective. You need a target cell or objective function cell that you reference here. In our case, that is K26. Then you choose your objective, max or min. And we're minimizing our total costs that are calculating K26. You then need to tell it the decision variables, and that's D16 to D25. And so from the decision variables, we now need to add the constraints. So Solver is going to determine the value of the decision variables that meet your objective, satisfying the constraints. So we need to add the constraints. The constraints are your left-hand side are related to your right-hand side, as we saw. And so first, let's add the net flow constraint. So we'll have that the net flow is greater than or equal to, and that's why I write the relationship here, our supplier demand. which is given by J30 to J36. Enter these constraints as blocks, or you can do them one by one. And so notice these will relate these cells correspondingly in these different arrays that we've entered here. So we'll go ahead and add that constraint. I have one other set. I need to know that the decision variables are less than or equal to the upper bounds. So D16 to D25 are less than or equal to C16 to C25. And that's it. We don't have any other constraints in our problem. We do want to make sure we include the non-negativity that we mentioned earlier. That's by clicking this box. This is a linear programming problem. You can solve it as a nonlinear, but I recommend if you know it's linear, choose the linear solver, which is simplex LP. It's a little bit more efficient. And then hit solve. So if you get a solution, you'll get something like this all in black. So solver found a solution. And so that's kind of the message we want to see here or here. And then we'll hit OK. And so notice that we do get our solution here. Our optimal solution shows up here. So we'll want to ship 6 units from vendor 1 to warehouse 2, 6 units from vendor 2 to warehouse 1, and 4 units from vendor 3 to warehouse 2. Then the factories will pull their shipments. Warehouse 1 will supply factory 1, and then warehouse 2 will supply both factories 1 and 2 with the following shipments to meet their demand. And this is for a total cost of $374,460. Okay, so this is the solution. So once you build this, you get the solution of the optimal shipment. Okay, and so here's our optimal solution, kind of here as well. Just I have that as a separate tab. What can be interesting is to look at this and do sensitivity analysis. So the question is, what if? Okay, so one of the things that's very interesting and powerful with these mathematical programming or spreadsheet models is we can start doing sensitivity analysis. We can do these what ifs. What happens if things change, if shipping costs or purchasing costs change, and we can rerun the model and see if the optimal shipping patterns change and our total costs change, okay? One of the easiest ways to do this is directly change the parameters in the model. And it's one of the reasons I bring these parameters, these numbers directly into the spreadsheet model instead of programming them directly into cells and formulas. Another option is to use the sensitivity report. And so what I did is I leave that for your discovery in terms of, there's a video here that for YouTube, which provides a nice overview of the sensitivity. And I also provided 2 links that are kind of short articles that provide some examples and interpretation of the sensitivity report and the information that comes out in that. If you're looking at changing one parameter at a time in your model, the sensitivity report can be useful. But if you're changing more than one, you need to rerun the model, which is what we're going to do here. So what would happen if transport costs increased for vendor 2 by $100? And so if vendor 2 here is here, so what we're looking at is increasing our transport costs here. So notice they're 450 and 500. So this is the same model. What happens if this goes up to 550 and 600? Based on the current shipping pattern, our costs would go up to $375,060. The question, though, for us is, can we do better than that given these costs have gone up? And so to do that, solver's already built in. It's pretty straightforward. Change those parameters, rerun the model. And notice for us what happens. So if you look before in the prior model, we had a shipment of 6. We were shipping 6 units from vendor 2. Notice now what happens with the sensitivity is we no longer use vendor 2 with the increase in cost, and we're pulling those 6 units from vendor 2 now from vendor 3. And what's even more interesting is costs only go up by $300 by doing that reallocation instead of $600 if we stuck with vendor 2. So it's not a huge cost savings, but we do save some money here. And you can see kind of the power behind those what ifs to see the changes in those shipping patterns and what happens to your total costs. And Randy, this also comes back to where you were asking, we could also play with these upper bounds as well in terms of looking at the impact of those on the model. Sorry, Dustin, I missed your question. Dustin asked if you had a cost associated with the warehouse, can you add that as a purchase cost for the final arc? So yeah, if there was a fixed cost, say for your warehouse for each unit coming in, so a handling fee, yeah, you could either add that in or add another column, Dustin, into the model, building that in. And so and it's a great question because usually we have inventory and storage costs that could be added here, which is not directly incorporated into this model. One of the other things that's interesting is sensitivity is not just about changing the parameters. It might be saying, well, what happens if we had another method of transportation? So the last tab here kind of does that. So expanding the model. So let's assume that the vendors have a second option to ship, that they can move their product also by rail close to the warehouse and then move from the warehouse and then from the rail to the warehouse. Let's just, for simplicity, assume they can do this at a flat rate of $600 per shipment using the same railroad. So how do we build this into the model? To build this, in essence, what we're doing is adding 6 additional arcs into our net flow diagram. So in essence, instead of one arc, we have one arc for each mode of transportation, one for truck, one for rail. And so that adds 6 additional decision variables into the model. So now I have my arcs for truck to the warehouse, and I also can move by rail to the warehouse. So now I can consider 2 modes of transportation. And so I build that information in here into my objective function using the same setup to minimize the total cost, which is that sum product. In terms of here now, my constraints here don't really change, just my sum ifs, remember, expand for my inflows and outflows here. And so still the same formulas. And so I still have since the number of nodes didn't change, I still have one node or one net flow constraint for each node. What did change is how I have to build in the upper bound constraints for the nodes between the vendor and warehouses. Because there's now 2 methods of transportation, I can no longer just put an upper bound here of 6, because it's the sum along this arc and this arc that has to be less than or equal to 6. And so I built that down here using a sum ifs command, or you could just add the 2 decision variables and make sure that's less than or equal to that upper bound. And so this was just expanding on that model. And so if you go into Solver, I kind of already built this out in Solver. So we're minimizing our objective of total cost, choosing min. Our decision variables have expanded to include the new 6 decision variables here. I've included the additional, broke out those additional upper bound constraints for between the warehouses and factories. And now we also have them down here between the vendors and warehouses. And still using the simplex LP and adding in, making sure I have my non-negativity so we don't make negative shipments. We solved that. And so now notice we get the following shipments. So now the only shipment, by adding in that optional extra ability to transport, we now have one shipment that goes along with truck from V1 to W2. The rest are then shipped by rail from vendor 3 to the warehouse to meet the order. And so now I can even consider multiple methods of transportation. And so this kind of completes the general I wanted to give you an overview and an example to walk through of how these models are built and solved and the usefulness of these. And I hope this kind of illustrates that, knowing that, yes, the example was a little bit simplistic. I wanted to have one that built some realness into it, but I think the other side of this is that these models can go very quickly and get very big and complicated. And that's one reason I kind of mentioned the Ilog software. Melissa S. asked, what if you are a producer and trying to figure out the most profitable way to sell or distribute your product? Would you reverse the network flow diagram, or would your decision variables change? I think in terms of, you can think of that way. In terms of you're selling or distributing your product, I think you're still thinking as you're the beginning point. If you're selling it or distributing it out to retailers and stuff, because you're still moving your product from you to someone else, in terms of looking at those methods of transportation, Melissa, in terms of that setup. So I still think you're in the same type of format. And you can even look at it in the reverse if you're the end person and you're actually paying those shipping costs. And so you can look at it that way as well. I don't know that the decision variables would necessarily change either. What's really interesting is you can really build and combine models here too. One thing I haven't done here, but I've done in other circumstances, is you could actually have like production problems set here with multiple products, what to produce, how to ship it. You could have separate individual math programming problems at each of these nodes as well. And then how do you move those products between the nodes based on the interaction of these different models? So you can easily make the models more complex. I don't know that that's always useful, especially if that's not really a question of interest. And I think in terms of, I agree with you, something that's really interesting here is this ability to compare these different transport options. And it may not even be rail, it could be different trucking companies here as well, that you can build in as well. So you can actually build that in. And there's a lot of nuances that can be built into these types of models as well, such as different type of pricing mechanisms. You could actually build in selling the product as well at a demand location and base this on total profit instead of total cost. And so there's different ways to approach that. So other questions people may have in the time we have left. So Randy asked, how do you model time? So that's a very good question. Within a logistics type of model, one way to do it like here is to do it for a specific period of time. You could combine this with a multi-period planning model where you'd have literally a separate net flow model or net flow diagram for each time period, and then you connect that with constraints or other variables that allow you to carry product from time period to time period. And so I think in terms of that, that becomes a very interesting question. Another way we've done it is we've actually had network flow models that model time individually within that and feed. We have different shipments coming in, but then they stay at transshipment nodes at different lengths of time. And so you can build in we've worked on a model for movement of piglets through a pig farm or swine operation through processing and stuff. And so that has to take time and dimensions. And those get a little bit more complicated in terms of keeping those dynamics. It's great, and time greatly increases the number of variables and size of the model. Ryan asked, have you used any other programs to run a linear model outside of Excel? So commonly, yes. So there's the Ilog, there's Excel. R will run these programs. I program in MATLAB and Mathematica. A lot of statistical software packages have optimization software built into them that can also run these. And there's a lot of other packages online. We have another one in our department called GAMS. There's another one called Lindo. And so there are multiple ways to build these models. Randy asked sort of a pooled panel approach. So I don't know if I'd call a pooled panel approach. Maybe that's a way to think about it, that you're bringing in all the time periods, but I don't know if I'd go to an econometric interpretation. I think it's a multi-period. It's just kind of, I think at the day is, are you tracking product over a whole production process over time, or is it meeting demands like in each time period of how you're going to set up that model? Other questions people may have? And all great questions. Thank you. Well, if there's no other questions, I would say we're right at time. I don't want to keep people on if they have other plans for their day. Thank you very much for attending and all your great questions. If you do have other questions, please feel free to email me. My email is Bergtold, BERGTOLD @ksu.edu. I'd be happy to answer any additional questions. Thank you very much for attending.
Thank you, everybody. And if you have another topic or skill set you'd like us to brush up on, please feel free to send me an email and let me know what that would be. Thanks, Dr. Bergtold.
Thank you.